So, welcome everybody. It's my very great pleasure to have Max Engelstein from University of Minnesota here, and he will talk about winding for wave maps. Please go ahead.
Thank you very much for having me. I hope everyone is doing well, or as well as they can be during these trying times. So I'll be talking about winding for wave maps. Maybe a couple caveats. First, all of this is joint work with Dana Mendelson, who's an assistant professor at the University of Chicago. Second, this is an area that I'm sort of coming into from the side a little bit. I certainly wouldn't call myself an expert on wave maps, so I apologize if I sort of don't cite correctly. Please feel free to correct me if necessary. And yes, please feel free to either ask questions in the chat or however things go here if something is unclear. Okay. Great, so let's get started. We'll be talking about winding for wave maps. And in case you sort of want to go away for a little bit and make yourself a sandwich and then come back later in the talk, let me give you a quick summary of what we'll be talking about today. So what are wave maps? They're wave equations which are constrained to lie inside of a manifold. Or if you don't like that and you prefer to think about things as being elliptic or stationary, they're harmonic maps, but where the domain is Lorentzian. Right, so there's a Riemannian metric plus a negative signature in the time variable. And one of the things about all energy critical equations, and certainly wave maps in certain dimensions, is that energy can concentrate at small scales. So after you rescale at these point of concentrations, what you get in the weak sequential limit is a bubble, which is just a harmonic map from sort of your spatial target, from sort of Rn to your spatial domain. And the big question of this talk is whether or not this bubble depends on the sequence of rescalings, right? So you pick a point in space-time that you rescale around, but if you rescale at certain zooms, like if you do 10 to the negative n, will you get one map? And if you zoom in at 2 to the negative n, will you get a different map? So this is a pretty fundamental question in these types of problems, and we'll connect it to a sort of similar question in harmonic map heat flow later in the talk. And what we do with Dana is we construct an example of non-uniqueness. So if you zoom in at 2 different scales, you get 2 different bubbles as the weak limit. And we think this is interesting because this is the first example of non-uniqueness in this sort of hyperbolic dispersive settings when it comes to bubbling. And sort of how does this work? Well, if you're from the elliptic regime and you're familiar with these types of results, you know that the target is going to be non-analytic. And this is sort of the crux of the whole matter. However, if you're familiar with the elliptic and parabolic results, first off, if you're not familiar, don't worry about it. I'll talk about them quite a bit. But if you are familiar, they can be a little bit misleading. You can't port things sort of right away from the parabolic setting to this sort of Hamiltonian setting. And we'll talk a little bit about why these settings are kind of different. And what's the inspiration here? Peter Topping has this very beautiful example of sort of a similar type of non-uniqueness for harmonic map heat flow. And I was talking about before, here we're in a Hamiltonian setting, which gives a lot of additional difficulties than the parabolic setting. Great. Okay, so let's start basic. Apologies if people know this already, but I certainly didn't. Let's start with a wave map. So a wave map is a map from R1 plus D, the 1 is for time, to some manifold. And they're critical points of this Lagrangian. And perhaps the thing to sort of keep in mind is that this Lagrangian doesn't have coercivity, right? It can be negative. So in particular, you're not thinking about like an elliptic minimization problem. However, you can always solve this problem. It's sort of a second year PDE exercise if the initial data is C infinity. But for rougher initial data, it actually involves quite a bit of advanced harmonic analysis. And there's some very important work of Kleinerman with Selberg and Kleinerman with Machiadon on this subject. You could write the equation of the critical points, the Euler-Lagrange equation in coordinates. I'm not really a geometric analyst, so I don't find this particularly illuminating, but here it is. So here you have the wave operator, and then here you have the Christoffel symbols for the target manifold, right? So these live with the metric G on M. And of course, this is a scalar system of equations. And why would you like to study wave maps? How is this helpful to you? Well, they're interesting in a number of ways. One of these ways is that when d equals 1, these model geodesics. They're also just a sort of natural nonlinear wave equation. They're a natural geometric flow. They have this relation to harmonic maps that we've already seen through bubbling. And then two things that I don't quite understand, but people always talk about. They give a simplified model of Yang-Mills and of general relativity when you have two killing fields. Okay, great. So these are sort of interesting objects that we might want to understand better. So let's start with a sort of basic example, which will give us a lot of insight into what's going on. We have a map from R1 plus 2 into the 2 sphere. In this example, the coordinates are a little bit simpler because we know what the Christoffel symbols are, and the equation looks like this. And we can make an additional symmetry assumption, which is that the map respects the rotational symmetry of the sphere. So this is what the equation looks like under this additional symmetry assumption. I hope you can see my screen here. And let me sort of draw a little picture to show you what's going on. So you sort of have R2, and then you have a sphere, which you could think of as living on top of it. And then what this map does is it sort of wraps R2 around the sphere, right? So this alpha coordinate is this like azimuthal coordinate here, and theta is this coordinate here. So this is sort of one of the simplest examples of a class of maps which still produce a lot of interesting behavior in the sort of wave map category. Okay, great. So let's keep thinking about equivariant sphere maps, or maps into the sphere. And there's one map which is stationary, which will play a super important role, which is this q lambda r equals 2 arctan lambda r. So in particular, this is a harmonic map, right? It solves the equation into the sphere, but is time independent. So what do I mean by a harmonic map? Just to remind us, harmonic maps, these are critical points to the Dirichlet energy. But now U goes from R2 to S2. And here, if you're an expert on harmonic maps, we don't need to worry about weakly harmonic maps versus minimizing maps or anything like that, because we're in R2. So everything sort of has the same level of regularity. If you're not an expert on harmonic maps, don't worry about it. So there's this beautiful result of Krieger, Schlag, and Tataru from 2008, which tells us the following, that there exists a wave map from R1 plus 2 into the sphere, which is essentially this stationary harmonic map rescaled depending on time, plus what I want to call an error. It's not quite an error because it doesn't go to 0, but in any compact subset of the plane, the energy of phi inside that compact subset goes to 0. And I'll be telling you a little bit more about what I mean by energy in a second. So this was a huge breakthrough because it gives an example of what's called blow up. We'll talk a little bit about why we have the terminology blow up here. But as you can see, you have something which is sort of nice and smooth. It's C infinity for all times that are positive. But as time goes backwards to 0, you get a sort of singularity at 0 because this term is going to 0, right? This is a positive power of t. There are other examples of blow up which were constructed in other sort of nonlinear dispersive models, not quite wave maps, by Raphael Rodniansky and Rodniansky-Sturvins. These are also really important results. Great. So to talk a little bit about what I mean by blow up, I'd like to talk about energy conservation and how it behaves under scaling. So associated to any wave map is a natural energy, which I've written down here. And the point of this energy is that it's constant in time. So already you see a huge difference from harmonic map heat flow, which perhaps you're more familiar with, where the energy decreases in time. This energy is conserved, right? And that makes sense. We're sort of in this Hamiltonian setting where we care both about kinetic and also potential energy. And it's a simple exercise to show that if U satisfies the wave equation, then so does this rescaled U. And indeed, the energy behaves like this under rescaling. And what's important to notice is that d equals 2 is a critical exponent, right? It means that the energy is invariant under scaling. So you can rescale your wave map and still get something which has the same energy bounds as the original map. So in particular, the energy of your q sub lambdas, remember that they're independent of t. So this is indeed the energy of q sub lambda. This energy is constant in lambda. It doesn't matter how much you're zooming in, but rather you still get the same number. And this is very important because if you're going to have an example of blow up, if you're going to have a wave map where this energy is conserved, but you can still look like q of r over lambda t, then it must be the case that the energy of these q r's over lambda t's don't blow up as lambda goes to 0 or infinity, because you have this energy conservation. So it's working in this d equals 2 setting, which we'll work in for the rest of the talk, which sort of allows this type of behavior to happen. And as we go down here, so going back to the Krieger-Schlage-Tataru example, right, which was this example from the previous slide, we see that if you take a limit of the energy inside this spatial region, which is getting smaller and smaller as t is getting smaller and smaller, this limit is positive. Actually, it's going to be equal to something like 2. And this is what we mean by blow up, that as you zoom in at a certain point in space-time, there's going to be positive energy left at that point, as opposed to 0, which is what you would expect if your map were smooth. So let's go back to some more energy concentration examples, right? We have this Krieger-Schlage-Tataru example of energy concentration at time equals 0. There's a much more recent example by Mohammed Pillai, who I believe is a recent PhD graduate, where you have energy concentration as time goes off to infinity. Here, the error term does something called scattering, which means that it satisfies a linear wave equation, a linearized version of the equation that U satisfies. And in fact, he constructs very particular examples which have this particular rate of blow up, 1 over log t. Notice that t is going to infinity now, so 1 over log t is still going to 0. And actually, he's able to construct blow up with a continuum of different sort of scaling factors. So how fast the blow up occurs. Jacek Gendry also recently was able to construct a slightly different example than equivariant. These are called K equivariant, where they wrap around the sphere K times, as opposed to just sort of wrapping around like this. They sort of wrap around K times and then also up. But he was able to show that you can get 2 bubbles which form at the same time and place. So here, this bubble is sort of happening at scale 1, and this bubble is actually concentrating. But both of them are occurring at time is infinity. And in fact, there is an equivariant example as well, where you have 2 bubbles which are sort of stacked on top of one another. This was done by Casey Rodriguez. It's a little bit more complicated to write out, which is why I haven't chosen to do so. And something very interesting happens with these examples that Jacek and Casey have constructed, which is that there's a rigidity in the lambda t. So unlike Pillai's examples, where you can get a continuum of different lambda t's, it turns out that the scaling factors associated to these 2 bubbles need to be very closely linked when 2 bubbles are forming at the same point. And this is sort of a really important fact. This is a breakthrough result by Jacek and Andrew Laurie in 2018. So what do all these examples have in common? Well, they look something like this. If you rescale the examples, right? So now you multiply the spatial variable by some lambda, and then you can also sort of scale the time variable the same way so that it's still a solution to the equation. They converge in a weak sense as time approaches the bubbling time to this Q of R, to this stationary harmonic map. And when our wave map does this, we're going to say that U bubbles off a copy of Q. Okay, so this is all an example of bubbling off Q. And in Jacek's example, you can actually bubble off 2 different maps depending on which sequence of scales you zoom in on. right? So if you zoom in at the constant sequence of scales, you'll bubble off this one. And if you zoom in at the t to the -2/k-2 sequence of scales, you'll bubble off this one. And notice these maps are different. One comes with a minus sign and one comes with a plus sign. Okay, so what's going on here? Well, there's this groundbreaking work of Sturbatz-Tataru, which tells you that at every point in time, a dichotomy occurs. Either you have energy concentration, or you can continue the map smoothly in a space-time neighborhood of that point. And if you have energy concentration, then there exists a sequence of points and a sequence of times, and the difference in the, and a sequence of scales, which goes to 0, such that if you rescale the map like this, it converges in an H1 loc weak sense to a harmonic map. Now, here I'm lying to you a little bit, or I'm simplifying things. Omega isn't quite a harmonic map because the wave equation has some additional symmetries. There's one symmetry that links space and time, which is the Lorentz transform, which you might know from general relativity. So really, you have this convergence to omega, where omega is in a Lorentz transform of a harmonic map. There's an infinite time version of this. And in the infinite time version, it says that there's a dichotomy. Either you have this bubbling, which I'm describing here, or the map scatters. So it approximates the solution to the linearized wave equation. So in the long time setting, you either get sort of linear behavior or you get this energy concentration. I want to talk a little bit more about this. In particular, I want to draw a picture. So what is this light cone that I talk about here? So you can imagine this is x minus x naught equals t naught minus t. That's what these lines I've drawn are here. So this is a cone. And this sort of, we're renormalizing so that the speed of light is 1. And what it's asking is, if you restrict the energy to happening on these time slices, is it true that the limit is 0, or is the limit positive? If the limit is 0, you can continue smoothly past this point. But if the limit is positive, then you get this type of bubbling behavior. Cool. So this is a characterization of bubbling and how it relates to energy concentration. Maybe at this point I should ask, are there any questions? Are things sort of clear here? Great.
Is there anything known if this is higher dimension, like a version of this, when you probably have like higher dimensional points of concentration?
Yeah, if your target, or sorry, if your domain has more dimensions, then I believe you're in the energy supercritical mode. So simply by rescaling, you can induce blow up, right? So the energy doesn't respect the sort of rescaling of the.
Yes. Yeah.
So a lot sort of nastier behavior can occur in higher dimensions.
Okay. Okay.
Yeah, that's an interesting question. Yeah, great. If there's nothing else, then I'll sort of move on to the next one. Thank you for the question. So to continue more about Sturbatz and Tataru's theorem, we have this dichotomy. Either you have energy concentration or you can extend smoothly. In our talk, we'll be looking at certain symmetry classes, which will rule out Lorentz transforms. So don't worry about them. I just included them to be complete. And if you can rule out bubbles for some topological reason or some energy reason, then you can guarantee that the solution exists for a long time. So here there's a lot of work of Krieger, Krieger-Schlag, Struve, Tau, and Tataru, which are able to rule out the formation of bubbles through a variety of either energy theoretic or topological situations. So for example, if there are no non-trivial harmonic maps from R2 to your manifold M, maybe your manifold M has some sort of topology, then you can never bubble, and so you have long time smoothness in existence. Another corollary here is that if you have two bubbles forming at one point, like in Jasek's example, these two bubbles must form at non-interacting scales. So what do I mean by that? In this weak limit, you only see one bubble. So if there's another sequence of RNs, which gives you a second bubble, omega prime, it must be true. So maybe, if there are some SNs which lead to omega prime, it must be true that sort of Rn over Sn goes to 0 or infinity, that these two bubbles don't see each other in the limit. And this should be familiar behavior for people who have studied bubbling in the setting of harmonic maps, for example, or other sort of energy critical elliptic equations like the Yamabe problem. The big question here is, how does omega depend on the sequence of times, Tn, that we pick, and the sequence of scales, Rn, that we pick? So this is the question of uniqueness that I alluded to at the beginning of our talk. Can you get different omegas if you look at different sequences Tn? And you can already see that this is actually a hard question to sort of pose formally, because you can get different omegas if you zoom in at different scales, but that's not really a question of non-uniqueness. You're just saying that there's sort of a bubble tree at that point, several bubbles forming in the same point at non-interacting scales. So really what you want to ask is if you can continuously pick the rescaling factor with the time such that you get convergence along the full time spectrum, not just along the sequence of times. That's sort of how to formally pose this question of a uniqueness of bubbling at a certain point along a given set of scales. So this is a little bit tricky, but deserves mention. Okay, so it turns out that there's this huge conjecture in dispersive equations which suggests that not only should you have uniqueness of bubbling at any given point in time, but that actually you should have uniqueness of the full bubble trees. So I've written out this soliton resolution conjecture in the setting of wave maps, and I haven't talked about things like Lorentz transforms and so on and so forth. But what it says is, imagine that you exhibit the energy concentration at a point x0, t0. Then there should be a sequence of harmonic maps which live with a sequence of scales such that if you zoom in at a given choice of scaling, you get that particular harmonic map. And then what should be left over? Well, some sort of error term, which is going to be smooth at the point. And probably its energy should sort of vanish locally. So here is sort of the dispersive analog of having sort of a bubble tree, a bunch of bubbles on top of one another. And this notation here says that we want the scales to not interact, which we had talked about on the previous slide. So if you'd like, this is telling you that the behavior that Jacek exhibited, right, where you had these two bubbles, is actually sort of the only thing that can happen, is that at a certain point, you can have a bunch of bubbles that stack up on top of each other, but each of them live with a certain scaling factor. It doesn't matter what times you approach the blow-up time with. And then what's left over is some sort of radiation term. The soliton resolution conjecture has analogs for a lot of different nonlinear dispersive PDE, KdV, nonlinear Schrodinger, the Yang-Mills, nonlinear wave equations. As I was saying before, this is a version which is simplified. So we're not allowing the point x0 to move around, and we're not including Lorentz transforms. All of that complicates the picture quite a bit. And so I should say, and perhaps this is not surprising, is that there's been quite a bit of progress on proving the soliton resolution conjecture up to a sequence of times. So if you allow this dichotomy, or sorry, this equation to hold for some Tn, where Tn goes up to T naught. And perhaps this shouldn't be so surprising that this would be the first push here, because you can imagine that certain like compactness and concentration compactness type approaches would help you prove a sort of sequence of time soliton resolution. So here there's very by Raphael Cote, by Grinnis, and by Ja and Koenig, all in the setting of wave maps into spheres or into surfaces of rotation. Proving that this decomposition exists for all time is really, really hard, and there's almost no progress towards it. There's this beautiful work of Jacek and Andy that I talked about before, which shows that if you have two bubbles and that your energy is at the level of two bubbles, then you have this sort of soliton resolution. There's work of Cote, Koenig, Laurie, and Schlag, which says that if you only have enough energy for one bubble, then you have this expansion. But in that setting, things are greatly simplified, right? Because J equals 1. But still, it's a very impressive result. And there's work of Ducaerts, Koenig, or Ja, Koenig, and Merle, which does similar things in the radial nonlinear wave equation setting. Let me be more precise. This first work I talked about, Cote, Koenig, Laurie, and Schlag, had this assumption of equivariant symmetry, whereas the Ducaerts, Ja, Koenig, and Merle drops the symmetry assumption, which makes things more complicated because there can be a lot more sort of symmetries inside of the map Q, so these Lorentz transforms and such. But again, both of these results only allow there to be one bubble forming at a certain point in time because of energy constraints. So still being able to prove this for multiple bubbles at a point in time is really quite complicated. There's a lot of work on this in a variety of settings, so I'm sorry for not citing more comprehensively. I should also say there is a very recent preprint by Ducaerts, Koenig, and Merle, which proves full soliton resolution for the radial nonlinear wave equation. So that's a huge sort of achievement in this field. But there's still a lot we don't know, especially in the context of wave maps. Okay, we're about halfway through the talk, which means that I should probably state a theorem of my own. So here's the main theorem from myself and Dana Mendelson. We posted this on the archive earlier this summer. And it says, there exists a smooth, up to the bubbling time, symmetric, and I'll tell you what I mean by symmetric, wave map, which goes from R1 plus 2, so we have the critical dimension, to a product manifold, and I'll tell you more about this product manifold in a second, but it's not too complicated. It's a torus across a sphere. But it develops a continuum of different bubbles at the origin as we approach the bubbling time. So depending on which sequences of times we take, we'll get a continuum of different types of bubbles. So what does this mean? It means that the full soliton resolution conjecture doesn't hold in the setting of wave maps without some additional assumptions, probably on the target manifold. Here, we see that F is C infinity, and probably we'll need the target manifold to be analytic in order to prove full soliton resolution. I'll talk a little bit about why that's an important distinction later. This proof actually doesn't give just one solution, which exhibits this weird behavior, but it gives a family of solutions. But still, it's a codimension, like it's a family of solutions with high codimension. So it's not necessarily a stable situation where you can perturb the initial conditions no matter in any which way and still get this bubbling phenomena. What do I mean by symmetry? Well, we can write the map pretty explicitly. These are the W and Z coordinates which live in the torus, and they just depend on the radial directions, right? So they're radial symmetric. And then the part of the map that maps into the sphere is equivariant, right? Remember, we have this situation where the plane maps up over the sphere. So this is the alpha angle, and this is the theta angle. So these are sort of highly symmetric maps. We call them quasi-equivariant as opposed to equivariant. And another thing is that the energy of this map isn't particularly high, and it's not as if there are many bubbles which are forming at this point in time. In fact, if we let E sub squiggly n be the smallest energy of a non-trivial quasi-equivariant harmonic map from R2 to n, right? So it's the smallest energy of a bubble that could occur in this symmetry class. Then EU is just above the energy of E squiggly n. So that means that there's just enough energy to form one bubble, but no more. So it's not like what's going on here is happening due to weird energy considerations. This is pretty much the simplest possible situation where bubbling can occur in this target map, in this symmetry class. I'm going to abuse notation or abuse terminology and call this energy, En, the ground state. This is usually reserved for the lowest energy of a non-trivial harmonic map, no matter what the symmetry class. But since we'll be working inside of the symmetry class, I don't think it will cause too much confusion. Okay, so this is our main theorem. Are there sort of any questions about what's going on here? Great. If not, let me talk a little bit about how this compares to Toppings' work on harmonic map heat flow, and then I can tell you a little bit about some of the issues in the proof. Okay. So Topping has done some very nice work on harmonic map heat flow. That's kind of an understatement. So let me try to remind you what harmonic map heat flow is, and I apologize again if there are experts in the audience. We have this energy, EU, which is exactly the Dirichlet energy, but constrained to lie inside of this manifold, right? So U goes from R2 to some manifold M. And then we look at the heat flow, which is almost like the wave map equation we saw before, but it's a parabolic equation as opposed to a wave equation. And there's this beautiful theorem by Topping from 2004, which shows that you can exhibit the same type of non-uniqueness for bubbling for harmonic map heat flow. So his target manifold is almost exactly the same as ours, and we'll talk about that a little bit. And he shows that there's this harmonic map which exhibits a continuum of different bubbles at the origin as t approaches the bubbling time. So in the elliptic parabolic setting, this sort of type of non-uniqueness has been known for a while. There was an example due to Brian White from 1992, where he showed the non-uniqueness of tangents for harmonic maps. So harmonic maps in higher dimensions aren't always smooth. And at points where they're not smooth, you can zoom in and get what's called a tangent map. So this is a stationary elliptic setting. And Brian White was able to show that you can construct an example which has a continuum of different tangent maps as you zoom into this one isolated singularity. And then Topping, in an earlier paper, was also able to show that this non-uniqueness can happen as t plus is equal to infinity. Due to certain energy considerations, you can't really have, this isn't happening because of bubbling, but sort of the limit map as time goes to infinity is not unique. You approach different sort of stationary limits as you approach infinity at different times. And I should say that at the core of all of these theorems is the same crucial example, which we'll talk about in a little bit. I don't say this to minimize their work at all, but just to say that somehow these are all C infinity as opposed to analytic examples, and they basically use the fact that a C infinity function doesn't have a Taylor series that it's necessarily equal to. And this is sort of the key aspect of what's going on. I should say that Topping actually does a lot more in this paper, some of which is really, really important to the theory. He gets bounds on the rate of bubbling, so the sort of rate in which this lambda factor concentrates, and he gets a bound at the first time in which bubbling has to occur. And Dana and I cannot do this in the dispersive setting, and hopefully I'll have some time to tell you why we can't do this. Topping invents a mechanism to prove non-uniqueness, because as we talked about before, multiple bubbles can appear at the same point in time, but at different scales. And we don't want that to count as non-uniqueness. We want to say that there is sort of no unique choice of scale with time that gives us a bubble. So Topping invented this idea called winding, which allowed you to test for non-uniqueness, or gave you a sufficient, although not necessary, condition for non-uniqueness. And we use the same winding terminology and mechanism. Okay. So let me talk to you a little bit about analyticity versus C infinity for parabolic flows. There's this theorem called the Voyage Inequality, which was invented, however your philosophical leaning, by Voyage in the first half of the 20th century. Voyage was a real algebraic geometer. So he was looking at these types of inequalities because he wanted to understand analytic varieties. And it says the following: you have a garden variety analytic function from Rn to R, and you have a point at which the gradient of this analytic function vanishes. Then there exists a constant C, a neighborhood of the point, and a gamma, such that the growth of the function is controlled by the gradient of f at y. And a corollary of this inequality, which seems kind of innocuous, is that if a gradient flow is bounded and f is analytic, then the long-time limit of the gradient flow exists, right? So this limit as t goes to infinity of x of t exists. You should think of gamma as sort of measuring the first non-zero term of the Taylor expansion of f at x naught. So if the Hessian of f at x naught is non-degenerate, then gamma is going to be 2. And if you have to go all the way to the 100th term of the Taylor series expansion of f at x naught to get something which is non-degenerate, then gamma is going to be way closer to 1. So as I said, Voyage is a real algebraic geometer. A key insight in the worlds of geometric analysis, which perhaps I'm speaking to the right crowd here, is that Leon Simon realized that you can prove an infinite dimensional version of these Voyage inequalities for gradient flows of some elliptic functionals. And this allows you to talk about either the long time behavior or even the infinitesimal behavior at singularities of certain elliptic and parabolic problems. So for example, in this paper, Leon Simon showed that isolated singularities for minimal surfaces always have unique tangents using the Voyage inequality. And these are sometimes referred to as Simon-Voyage inequalities, these infinitesimal analogs, or sorry, infinite dimensional analogs. Great. So for C infinity, things are very different. There are C infinity functions that vanish to infinite order. I've written one down for you here, and your calculus students can maybe do this as well. And as a corollary, you can write down C infinity functions such that the associated gradient flow is bounded, but has a continuum of different limits as t goes to infinity. Leon Simon calls this the goat tracks example, because I guess here's a goat which is walking up the mountain, and it sort of spirals over and over and over because it doesn't like to go sort of straight up. And so it actually has a whole level set of limit points as the time goes to infinity. So here you can see in the parabolic setting, very different behavior in the C infinity versus analytic regimes. But we need to be careful. Okay, so sorry, let me take a break here. Are there any questions about sort of this different C infinity versus analytic behavior? Maybe let me state briefly that it's this sort of example of a C infinity function which vanishes to infinite order, and this sort of goat tracks example, which lies at the heart of Toppings' examples of non-uniqueness and Brian White's examples of non-uniqueness. Of course, it takes quite a bit of work to actually bake them into the problem that you want. This will also be at the heart of my example of non-uniqueness with Dana. But I should say that one needs to be kind of careful applying these parabolic lessons to the Hamiltonian setting. For example, it's not true that if you have an analytic function which is driving your Hamiltonian flow, then you have a unique limit as time goes to infinity. Here's a very easy example of an analytic function where if you look at the associated Hamiltonian flow, you get something which circles around and around and around and around and around as time goes to infinity. Part of the issue in the Hamiltonian versus the parabolic setting is that critical points are not barriers. So for example, if you look at a parabolic flow, which is generated by this function f, then once you hit the circle r equals 1, you stop. That's because the stationary solution, where r equals 1, is a barrier to this parabolic flow, right? The gradient vanishes at that point. And so the parabolic flow can't sort of push through that barrier. But there's no maximum principle in Hamiltonian PDEs. And so, in fact, you can have a Hamiltonian flow generated by the same function, which is bounded, but which has no points on the circle r equals 1 as limits as t goes to infinity. And somehow you should think that in the Hamiltonian setting, we pay attention not just to the kinetic energy, but also to the potential energy. And so things can sort of have enough potential energy to sort of break through these barriers, even if they don't have enough kinetic energy to do so. Great. So we can see here that we can't just sort of immediately port this sort of Wojciech C infinity versus analytic framework to the Hamiltonian setting. And that's what we're working with when we're working with wave maps. So let me tell you a little bit about the target manifold. I've been a naysayer now about how this might not work. Let me tell you about how it actually does work. So we have this product manifold, which is the torus across the sphere, with this warping factor F. And here's the warped metric. You can tell that I'm not a geometer because I think I'm missing a squared up here. If I was a real geometer, I would have written that. I apologize. I'm secretly an analyst in disguise. This is the standard flat metric. Oh, sorry. This metric H on the torus, we're going to pick very carefully to make a certain curve on the torus into a geodesic. And we're also going to pick this function F to be a C infinity function, which vanishes to arbitrarily high order. So indeed, H is an analytic metric, but it's chosen so that this particular curve is a geodesic. And if we look at this curve on the torus, what does it do? If this is sort of the W direction and this is the Z direction, as S goes down to 0, it starts to wrap around more and more rapidly and wraps around infinitely often as we go down to 0 here. So as I was saying before, this curve gamma winds around the line W equals 0 infinitely many times as S goes to plus and minus infinity. Sorry, I said S equals 0 before, but I meant W equals 0. We pick F very carefully so that the gradient of F always lies parallel to gamma, and the minimum of F occurs on this circle W equals 0. And F is also going to be a bounded function. And this, of course, if you think about it for a little bit, is only possible if F is non-analytic. Because if you looked at the gradient flow generated by F, it would just follow gamma. And so it would have the curve W equals 0 as a limit curve. So it wouldn't have a unique limit point, and by Wojciech, this means that F can't be analytic. And indeed, F looks something like e to the negative 1 over x. So this looks a lot like the goat tracks example. What's important to note is that because of this gradient of F being parallel to gamma, this submanifold gamma cross S2 lies geodesically inside of the entire manifold, which means that a flow which starts inside of this submanifold stays inside of it for a whole time. And that's how we're able to control the sort of behavior of the flow. Topping, if you know his example, has a very, very, very similar setup. His gamma is the same, his product manifold is the same, his F is almost the same. But in our setting, there's an additional difficulty. Topping is able to constrain where the parabolic flow lives. And that's because he's working in a parabolic setting. So he's able to show that if the flow sort of starts close to the curve W equals 0, then it can't escape off in this direction. And so actually Topping's manifold is not a torus cross S2, but rather a cylinder cross S2, because he doesn't care what happens in this direction. And furthermore, he only needs to define his warping factor F near the manifold W equals 0. For us, there's no maximum principle. So it's possible that the flow could approach the curve W equals 0 from either side, right? Either by going up this way or down this way. That's why we have to work on a compact manifold like the torus, and why we have to define our F globally. And this involves a bunch of technical difficulties mostly. Okay, so you can already sort of see where the winding is happening. Let me tell you a little bit about this definition of a winding singularity. So this was invented by Topping, and what he says is that a singularity is winding if you have this weak limit in C0 from R2 to M, but that you don't have a weak limit along any subsequence if you lift your map from M to the universal cover of M. And you can sort of see how this involves winding behavior, right? Because if you have something which is a non-trivial element of the homotopy group of M, then when you lift it to the universal cover, things will be going off to infinity, as opposed to sort of staying and having a bunch of different limit points. So this definition is really clever. It captures a way to sort of formally describe what's going on when you're circling a drain, so to speak, but never going through it. So it's not hard to see that under our previous definition of having continuous time soliton resolution, if you have winding, you can't have this continuous time resolution. So what we're going to have is we're going to have these sequence of harmonic maps where we basically attach our favorite stationary bubble, which lives in the S variable, to different points on the circle W equals 0, right? So here's our torus. At each point on the circle, we attach a bubble which goes into this component. And each one of these maps is going to be a weak limit of our wave map. So in particular, if one of these maps is a weak limit of our wave map, then in fact all of them are, and the singularity is winding. That's because you have to go all the way around gamma to get to one of these maps if you started inside of gamma. Yeah, so let me sort of draw the picture again to try to make this a little bit more clear. Here's our gamma, which winds around and around and around and around. And here's our point, right? Which here's our Z0, and then there's sort of a sphere attached to it. So if you'd like, the wave map talks about an evolving map from this product, from R2 to this product. And what the map does is it has to wind all the way around before it can weakly limit to this point. So in fact, it must have also weakly limited to all of these other maps also. And you can make that formal using a little bit of topology and some analysis. So this is going to be our non-uniqueness that we see. Cool. So I think in the little bit of time I have left, I can tell you a little bit about the sketch of the proof. Am I doing okay on timing, by the way?
Yeah, 5 to 10 minutes.
Perfect. I'm not going to need that much time. Great. Okay, so let me tell you a little bit about the proof. Of course, at this point, you can zone out if you've gotten what you need to from the talk. So we construct this manifold, and we take smooth initial conditions, which are contained inside of our gamma cross S2, and in fact, inside of the tangent bundle, because we want sort of the time derivative at time equals 0 to be moving in the direction of the geodesic. We don't want to push ourselves off the geodesic immediately. And here, we need to define the metric twist globally because we're not sure. We know it in the long time, we want to be wrapping around W equals 0, but it's possible that we'll go all the way up to close to W equals 1, or even that we'll wrap around W equals 0, but from sort of the bottom, if you will. This is a difficulty which is not present in Toppings construction. And then we now want to show that bubbling does occur. If you remember way back earlier in the talk, there's this dichotomy. It's possible that as time goes to infinity, you can have what's called scattering, where you approach the solution of the linearized wave equation. And what we do by using ideas of Christodoulou and then Tabla d'Arzadeh, is we show that energy concentration has to happen either at a finite time or as time goes to infinity. And that means that bubbling has to occur. This part is completely different than Toppings' proof, where he's able to show that energy concentration occurs due to topological considerations. We're not able to make that work in our setting for a variety of technical reasons. Yeah, so in particular, if bubbling doesn't occur for harmonic map heat flow, then you have relaxation where you limit to a harmonic map. And he's able to show that such a harmonic map with the right boundary values don't exist. For us, we don't necessarily have relaxation, right? Your long-term limit can be something that still depends on T because the energy doesn't strictly decrease. Again, we're able to use this total geodesicness to show that the flow can't leave the manifold that we care about without bubbling. This is slightly difficult because we don't have barriers. And then we're able to show, because of our energy considerations, that any bubble which appears inside of the sort of allowed zone must be one of the bubbles that we like, one of the bubbles that's on the circle W equals 0. And here we're actually using the conserved energy to our advantage because we're able to rule out higher energy bubbles because we have this sort of energy conservation. And then finally, as I've talked about more immediately and at length, the topology of gamma, the fact that it represents a sort of non-trivial term in the first homotopy group of the target manifold, tells us that the singularity is winding, and thus we don't have soliton resolution into this particular domain. Okay, I think that's my time. Thank you very much for listening and giving me some of your August time. Thank you very much.
Thank you. Are there questions? Remarks, comments? Scrolling through, somebody's unmuting themselves because. So I have one, maybe I start. So do you think you disproved this conjecture, I forgot the name, for in the non-analytical case of the target manifold? But you said essentially this Voyage inequality doesn't show that in analytic it would work. So do you think the conjecture is false also in the analytic case?
So this is very complicated. I think it's hard to say. Maybe I can speculate a little bit and no one can hold me to it. There's some indication that if you have bubbling and you go inside the light cone, your behavior starts to look more parabolic or elliptic than it does Hamiltonian. I cited a paper by Grinnis earlier in the talk, which really utilizes this perspective on wave maps. And then if you look more elliptic, you might imagine that these Voyage tools can actually be quite helpful. So the problem is that if you have purely Hamiltonian dynamics, Voyage doesn't give you anything. Okay, that's very nice and good, but in the very few settings in which we've proven uniqueness, like the soliton resolution conjecture, this type of Voyage approach hasn't worked out at all. It's a little bit hard to say if that's because we're working in settings where we already have a lot of symmetry, and so we sort of know a little bit more about the behavior near these bubbles, or if that the Voyage approach is always doomed to fail. I think it's kind of unclear.
Very interesting. Okay, any other question? Maybe I stop the recording.